Whenever movement takes place between surfaces that are in contact with each other, friction, or resistance to the movement, occurs. Friction between the moving parts of industrial equipment can cause excessive heat and wear. So lubrication is used to help reduce and control friction. Lubrication is the act of applying a substance called a lubricant that creates a slippery barrier between surfaces that would otherwise come in contact. In this part, we'll look at some of the types of friction that can occur. We'll also look at different kinds of lubricants and describe various levels of lubrication. Moving parts generally experience one or more of three basic types of friction: sliding, rolling, and fluid. Sliding friction occurs when one surface slides across another. This type of friction offers the most resistance to motion, so machines are usually built to minimize or eliminate it. One way of building a machine to minimize sliding friction is to place rolling elements between the moving surfaces. This is the principle behind rolling contact or anti-friction bearings. Although rolling contact bearings are used to reduce sliding friction, they do experience another type of friction, rolling friction. Rolling friction is the resistance to motion that occurs when one object rolls over the surface of another. Rolling friction is considerably less severe than sliding friction, but rolling contact bearings must still be properly lubricated to reduce heat and wear. Another way to reduce sliding friction is to separate two sliding surfaces with a film of lubricant. As long as the surfaces don't touch, sliding friction is eliminated. Some fluid friction exists within the lubricant, but it's much less than the sliding friction. Fluid friction is the resistance to motion that exists in a fluid. For instance, fluid friction is what makes it difficult to walk rapidly in deep water. Three common kinds of lubricants are liquids, greases, and solids. Liquid lubricants are oils, mineral oils, which come from refined crude oil, and synthetic oils, which are man-made compounds, are commonly used in industrial applications. Greases aren't strictly liquid or solid. Instead, they typically soften when the temperature rises and stiffen when the temperature falls. Solid lubricants are made from substances that retain their shape under normal conditions. Solid lubricants include some forms of metal, such as molybdenum disulfide, and several solid chemicals, such as graphite. When they act as a lubricant, the solid materials create layers that slide over one another. This reduces the friction that would occur if metal parts were in direct contact. Solid lubricants, such as the material whose trade name is Teflon, are also used as chemical coatings that prevent metal-to-metal contact by providing a solid covering for a metal surface. Chemical coatings are generally used in combination with another kind of lubricant. For example, if an oil film breaks down and allows two surfaces to come in contact, the chemical coatings provide backup lubrication. Different levels of lubrication are possible. One level is no lubrication. When there's absolutely no lubricant between moving surfaces, the surfaces are dry. This condition causes the maximum friction between moving surfaces and should be avoided as much as possible, except for applications such as braking, in which maximum friction is desired. A second level of lubrication is mixed film lubrication. To better understand what happens when this occurs, we'll use this illustration that shows a highly magnified portion of two mating surfaces. Under magnification, you can see that the mating surfaces actually have many irregularities, or peaks and valleys. Mixed film lubrication occurs when the mating surfaces are only partially lubricated, and metal-to-metal contact occurs between the high points of the surfaces that are moving across each other. Part of the load is relieved by the lubricant, but the high points of the mating surfaces take most of the load, which results in friction and wear of the surfaces. Mixed film lubrication is by no means an ideal situation, but it is a common occurrence. A third level of lubrication is film lubrication, also called full film lubrication. It occurs when moving and stationary surfaces are separated by a film of oil. Film lubrication is the preferred level of lubrication for bearings. To see the basics of how film lubrication works, we'll use this illustration of a plain journal bearing. The bearing has a sleeve that surrounds a shaft. The space between the bearing and the shaft contains lubricating oil. While the shaft's at rest, the weight of the shaft squeezes most of the oil out from between the shaft and the bearing. This places the bearing and the shaft in metal-to-metal contact. But when the equipment is started, the shaft begins to roll slowly, and the motion drags oil underneath the shaft. Oil sticks to the shaft as the shaft turns, and the oil is carried between the two surfaces. The shaft is lifted away from the surface of the bearing by a film of oil. As the rotational speed increases, more and more oil is drawn under the shaft, and eventually, full film lubrication is achieved. The layer of oil supports the shaft and prevents it from touching the bearing surface. In this part, we'll examine some of the most significant properties of lubricants. One of the most critical properties of liquid lubricants is viscosity. The thicker lubricant has a greater resistance to flow, so it has a higher viscosity, while the thinner lubricant has less resistance to flow and therefore a relatively low viscosity. The thinner the lubricant, the lower the viscosity. Viscosity is affected by temperature. Higher temperatures cause lower viscosity because lubricants thin as temperature increases. On the other hand, lubricants thicken as temperature decreases. Both cases are significant because a lubricant won't lubricate properly if it's either too thick or too thin. If a lubricant is used where large changes in temperature occur, the lubricant's viscosity index is important. The viscosity index is a measure of the lubricant's viscosity change in relation to temperature change. If, when temperature changes a large amount, the lubricant's viscosity changes a small amount, the lubricant has a high viscosity index, or VI. If, when temperature changes a relatively small amount, the lubricant's viscosity changes a large amount, the lubricant has a low VI. Consequently, the temperature at which the viscosity measurement was obtained must be stated. This information is important because the same lubricant will have different viscosities at different temperatures. In addition to viscosity, several other properties that affect lubricant performance are used by manufacturers as they develop lubricants for various applications. One of these properties is pour point. It's the lowest temperature at which a lubricant will pour or flow. Below the pour point, the lubricant will be too viscous or thick to flow by gravity. A low pour point indicates that the lubricant flows at low temperatures. A high pour point indicates that the lubricant needs higher temperatures to flow. The pour point is especially critical in machinery that must run in cold weather and in equipment that's used in refrigeration systems. Two other temperature-related properties of lubricants are flash point and fire point. The flash point of a lubricant is the lowest temperature at which the lubricant's vapor will ignite when it's exposed to a source of ignition. The fire point is the lowest temperature at which the lubricant will burn steadily when it's exposed to a source of ignition. This occurs because enough vapor is created to cause continuous burning. If either the flash point or the fire point is exceeded, a fire hazard exists. Resistance to oxidation is another significant property of lubricants. It refers to a lubricant's resistance to reacting chemically with oxygen when exposed to heat and air. You see, many industrial lubricants are made from hydrocarbons. When the hydrocarbons are exposed to heat and air, the chemical reaction called oxidation occurs. Oxidation causes chemical changes that destroy a lubricant's effectiveness and lead to the creation of deposits such as sludge and varnish. Oxidation also produces acids that cause rust and corrosion. The oxidation process is normally slow, and over time, most lubricants do tend to oxidize. Oxidation can speed up, however, if the lubricant splashes around excessively or if it's exposed to high temperatures. A lubricant's resistance to forming an emulsion is also important. Basically, an emulsion is a mixture or suspension of components that are difficult to separate once they've been combined. The process that causes the formation of an emulsion is called emulsification. A lubricant that resists forming an emulsion is usually desirable because an emulsion of lubricant and water has poor lubricating qualities. Equipment manufacturers generally specify appropriate lubricants for their equipment, depending on how the equipment will be used. In turn, workers are responsible for making sure that they use the type of lubricant that's been specified. Various factors determine the appropriate lubricant for a given situation. For instance, pressure or load affects the selection of a lubricant. An application with relatively high pressure requires a lubricant that won't flow away from where it's needed when the pressure increases, such as when gear teeth mesh. Applications that involve relatively high loads or pressures typically require greases, solid lubricants, or high viscosity oils. Speed is also a factor in lubricant selection because there's a higher rate of wear at high speeds than at low speeds. Generally, low viscosity oils provide lower friction and better heat transfer at high operating speeds than high viscosity oils do. In short, low viscosity lubricants are more suitable for components such as certain bearings where the loads are light, the speeds are high, and the system is fully enclosed. High viscosity lubricants are more suitable for components such as open gears where the speeds are low, the loads are high, and the system is not enclosed. Temperature also affects a lubricant's viscosity. If wide, rapid variations in temperature are involved, a lubricant with a high viscosity index is usually needed. Temperatures must not exceed the lubricant's flash point and fire point. On the other hand, temperatures must not be lower than the lubricant's pour point. Substances or conditions in the environment where a lubricant will be used also affect lubricant performance. For example, a lubricant must be able to withstand chemicals that may tend to break down the lubricant. And if there's water in a system, a lubricant that resists emulsification is usually required. In most cases, lubricants contain additives which also affect lubricant selection. An additive is a substance that's added to a lubricant to provide or improve a specific property. Such substances are usually added by the lubricant manufacturer. To make sure that they use the correct lubricant for a specific piece of equipment, workers usually refer to the lubrication chart that's supplied by the equipment manufacturer. The lubrication chart applies only to that particular piece of equipment, and it should not be used as a lubrication guide for any other equipment. Often, each lube point or equipment part that requires lubrication, as indicated on the lubrication chart, is shown and numbered on an illustration that accompanies the chart. In turn, the numbers from the illustration are listed on the lubrication chart, in this case, in the index numbers column. For instance, item number 2 from this illustration is identified as the boom pivot shaft on this simplified lubrication chart. Reading across that line on the chart, you can find the number and type of lube points. In this case, 2 grease fittings, and the recommended type of lubricant and method of application. In this case, multi-purpose grease, abbreviated as MPG, applied with a pressurized grease gun or pressure gun. You can also find out how frequently the boom pivot shaft should be lubricated, which is every 10 hours. Proper storage of lubricants is essential to prevent contamination and unnecessary waste of the lubricants, as well as fires, spills, and accidents. For these reasons, the federal government and many state governments have strict regulations that apply to the storage and handling of lubricants. In this part, we'll cover some basic procedures for ensuring that lubricants are stored safely. After lubricants have been delivered, they're often stored in their containers for a long time before they're used. Depending on a facility's available space, the containers may be stored indoors or outdoors. Two major problems with outside storage are dirt and weather. So store lubricants in a location where there's a minimum of dust and dirt. Also, use a temporary covering like a tarp or a permanent covering like this three-sided shed to protect the containers from the weather. Generally, metal drums of lubricant should be stored either upright on pallets or horizontally on racks that keep the containers off of the ground. You see, storing a metal drum on a rack keeps the metal of the drum from contacting the ground or standing water. This helps prevent the destructive chemical reaction of corrosion from occurring. In addition, storing a drum on its side prevents water from collecting on the top of the drum. Water that's allowed to collect here can eventually penetrate the seal around the drum's opening and contaminate the lubricant that's inside the container. Most lubricants are combustible, which makes fire a hazard that's associated with storing these materials. One reason for storing lubricants outdoors is to minimize the damage from a fire by keeping the lubricants away from buildings, equipment, and work, such as welding or cutting, that involve sparks or open flames. Also, always keep an appropriate type of fire extinguisher in the storage area. When lubricants are stored indoors, weather is less of a problem than with outdoor storage. But contamination, spills, and fire are still hazards that must be dealt with. Store lubricants in a fireproof room or building that's clean, well lighted, and well ventilated. The storage area should have a fire extinguishing system that can be controlled manually as well as automatically. Also, keep an appropriate type of portable fire extinguisher in the storage room. Position storage racks or shelves so that all lubricants can be reached easily. Make sure that all containers are plainly marked to identify their contents, and store the containers so that their markings can be clearly seen. If possible, store opened lubricant containers and containers of contaminated lubricants separately from new unopened containers. To dispense lubricant from a drum by gravity flow, store the drum in the horizontal position on a rack and equip the drum with a spigot that has a drip-proof valve for withdrawing the lubricant. If you must store a drum in the vertical position, you'll probably have to pump the lubricant out of the drum. Store cans or pails of lubricant neatly on shelves or on the floor. Finally, repair leaks promptly and clean up any drips or spills immediately. In this part, we'll look at common types of lubrication equipment for industrial applications. We'll begin with a grease gun. Hand-operated grease guns, or lever guns, are often used to grease bearings. Typically, the nozzle end of the gun is attached to a grease fitting on the bearing housing, and the gun's hand lever is pumped to apply grease through the fitting to the equipment's bearings. Grease guns enable you to develop high pumping pressure with little effort. In fact, grease guns can develop pressures in excess of 10,000 psi, which can damage seals. So you must operate grease guns with care. A very common way of filling some hand-operated grease guns is simply to slip a cartridge of grease into the barrel of the gun. Other types of grease guns can be filled quickly and easily with a filler pump that's clamped onto a bulk grease container, then attached to the gun. Power-operated lubrication equipment can be portable, like this pneumatic or air-powered grease gun. Or it can be permanent, like this centralized lubrication system that's designed to lubricate the bearings on several machines automatically. This illustration shows a typical centralized lubrication system. A motor-driven pump forces lubricant from a reservoir through lines in the system. A metering device on the lines measures out the correct amount of lubricant to inject for each bearing. Internal lubricators are typically used for the bearings of an internal combustion engine, an air compressor, or a gearbox. In this gearbox, oil is pumped from a reservoir through oil lines inside the machine. Then a gear that's mounted on a separate shaft rotates through the lubricant that's inside the gearbox and carries the lubricant onto the other gears. In this part, we'll talk about some standard procedures and precautions that are associated with handling and dispensing lubricants. Generally, when a lubricant is needed in a facility, workers move the lubricant containers from bulk storage to a central location in the facility where the lubricant can be dispensed. If a lubricant is taken from outside storage in cold weather, it should be allowed to warm up indoors before it's used. Low temperatures can thicken lubricants and make them unusable until they've been thoroughly warmed. As a rule, a lubricant container should be cleaned before it's opened to prevent dirt or debris from the container getting into the lubricant. When a container is opened and lubricant is removed, the container should be resealed as soon as possible to protect the remaining lubricant from contamination. Different lubricants may have incompatible additives, so when a lubricant is added to a partially full system, the type of lubricant that's added must usually be the same as the type of lubricant that's already present. When more than one lubricant is dispensed from the same location in a facility, it's important to identify each lubricant properly. Of course, the original shipping container must clearly state what lubricant the container holds. But any time a lubricant is placed in another container, the new container must also be clearly and correctly labeled. Lubricant should never be returned to its original container after it's been removed. That could contaminate the entire contents of the container. Likewise, contaminated or waste lubricant storage must be clearly marked. Different methods can be used to remove or dispense lubricants from their containers so that the lubricants can be put to use. We'll look at two of the most common methods for dispensing oil. One way to dispense oil from a drum or a barrel is to use a barrel pump that fits into the container. The first step in installing a barrel pump is to clean off the top of the drum. Then open the drum, and if there's a drum seal, remove it. Next, clean the pump and insert it into the drum. And finally, tighten the pump securely to the drum. For the barrel pump to work properly, the drum must be vented. This is usually done by removing a small vent cap from the top of the drum before you start to pump. When you're done pumping, replace the vent cap to prevent contamination of the lubricant. Another way to dispense oil from a drum is with a spigot that has a leak-proof valve. The drum must be positioned on its side. Sometimes, a drum with a spigot is placed in a rocking frame. To dispense oil from the drum, the frame is rocked forward so the drum lies on its side. The drum may then be left in this position until it's empty, or if necessary, it can be rocked back into the upright position. With the drum vented, open the spigot and withdraw the oil from the drum. When the desired amount of oil has been withdrawn, close the spigot and the vent cap. When lubricating oil becomes contaminated or can no longer provide adequate lubrication, it must be replaced with fresh oil. Oil is usually changed according to a schedule that's established by the equipment manufacturer. Also, in many cases, contaminated oil can be purified and reused. Oils are often divided into several common groups based on the uses for which the oils are suitable. One group of oils is circulating oil. Circulating oil flows or circulates through a piping system or moves freely within a closed area. The circulating oil group also includes hydraulic oil. Hydraulic oil is primarily used to transfer force from one component to another in a system. Sometimes, though, the same circulating oil is used for both lubrication and hydraulics. For example, large steam turbines are often built to use the same oil for lubrication and for hydraulic control. In equipment that's operated in low temperatures, a circulating oil's pour point must be low enough to allow the oil to flow freely. Also, the viscosity index of a circulating oil is very important if the system in which the oil is used experiences large changes in temperature. Gear oil is a type of oil that's used primarily for lubricating gears, although it may be used to lubricate many other devices as well. Various gear oils are available. A gear oil may be a straight mineral oil, or it may contain additives to improve the oil's load-carrying ability and its performance in high-pressure applications. Viscosity is a critical property for gear oil because an oil that's too thin will be squeezed out from between the gear teeth and won't protect them. But the oil must also be able to flow freely enough to help cool the gears. An oil that's too thick will cause the gears to overheat because of high fluid friction. Engine or motor oils contain additives that enable the oils to be used in different types of operating conditions and in different types of engines, such as diesel engines and gasoline engines. This tank truck, for example, uses an engine oil that's specifically designed for heavy-duty diesel engines and relatively severe working conditions. There are many different methods for lubricating equipment with oil. The method that's used generally depends on the equipment that's being lubricated. Manual oiling often involves wiping or brushing oil onto moving parts, such as chains and wire rope. To prevent personal injury when applying lubricants manually, workers must always use the appropriate personal protective gear. Workers must also make sure that the equipment is shut down and properly tagged and locked out before they apply the lubricant. Some bearings have a small oil cup or reservoir that dispenses oil automatically as the oil level in the bearing decreases. To maintain the proper oil level in the bearing, workers must check the level in the oil cup regularly and add oil as necessary. The oil cup should be cleaned before it's used. Dust and dirt that enter the bearing with the oil can lead to bearing failure. Centralized oiling is a lubrication method in which oil is automatically applied to the moving parts of several machines by an independent, centralized oiling system, such as the one illustrated here. But to be sure that the proper oil level is maintained, workers must check the level in the reservoir on a regular basis and add oil when necessary. Finally, applying oil to lubricate bearings is a critical maintenance task in most industrial facilities. One of the most common problems associated with lubricating bearings is over-lubrication. The application of too much lubricant can cause an increase in operating temperature and a decrease in viscosity. Then, if the lubricant becomes too thin, it can't carry the load inside the bearing. As a result, the bearing will fail and have to be replaced. Also, too much lubricant being forced into a bearing may burst the bearing seals. This in turn allows the lubricant to escape from the bearing while contaminants are allowed to enter. Certain properties unique to grease determine the appropriate grease for a particular application. One such property is drop point. Drop point refers specifically to the melting point of a grease. The term is derived from the method that's used to measure this property. The grease is heated slowly until fluid begins to drop from the grease. The temperature at which the drops form is the drop point. If the operating temperature in an area is higher than a grease's drop point, the grease tends to flow away from the area that needs lubrication. So a grease's drop point is normally considered the highest temperature at which the grease can be used. Some greases don't have a drop point. Instead, when heat is applied, the grease begins to decompose chemically before it reaches the point where the thickener in the grease would break down and drops would form. A grease's consistency or stiffness is an important physical property for much the same reason as drop point is. If a grease is too hard, it will be difficult to apply. But if it's too soft, it may flow away from where it's needed. Either of these situations could result in inadequate lubrication and damaged equipment. The consistency of a grease varies with temperature, and there's generally an increase in the softening of a grease as the temperature increases. For these reasons, consistency is a critical property to consider when grease is selected for a particular application. The American National Lubricating Grease Institute, NLGI, has developed a widely used classification system of grease consistencies. In this system, grease consistencies are designated by NLGI numbers that range from 000 for the softest to 6 for the stiffest. If a grease must be pumped through a centralized greasing system, the grease's pumpability should be considered. Pumpability is a measure of how easily a grease can be moved or pumped through a centralized greasing system without clogging the pipes or the components in the system. The water resistance of a grease is an important property if the grease will be used with machinery that can be damaged by water. Many greases break down or dissolve when they come in contact with water, but most greases that contain thickeners such as calcium or lithium soap, which are insoluble in water, resist water very well. The ability of a grease to retain its chemical and physical properties when subjected to extreme temperatures or exposed to reactive substances is referred to as the grease's stability. In many applications, it's crucial to use a stable grease to protect the equipment that's being lubricated. Bearing applications are especially sensitive to instability. If the grease in a bearing breaks down from the heat that's generated during operation, the grease will leak out and leave the bearing dry, causing the bearing to seize. A stable grease, on the other hand, resists breaking down due to temperature increases or exposure to air, water, or reactive chemicals. There are various reasons for using grease, most of which depend on the operating conditions in a given situation. Under certain conditions, grease may be necessary to ensure that the lubricant will stay in place. As long as grease remains semi-solid, it tends to stay where it's put. Oil is much more likely to flow away from where it's needed than grease is. Even when both oil and grease would flow out of an area, it's much easier to retain grease with a seal than it is to retain oil. Keeping the lubricant in place is important because leaking lubricant could contaminate surrounding areas or cause a fire hazard. Another reason for using grease is that grease may be required to assure that contaminants are prevented from getting between lubricating surfaces. In some high-temperature applications, such as this conveying dryer, grease with a high-temperature thickener is used to keep the lubricant in place. It's possible to use oil in high-temperature situations, but additional equipment, such as this cooler, must usually be provided to cool the oil. Greases are also used to lubricate bearings in low-speed applications that don't generate much heat. Grease is frequently used when the running speed of a plain journal bearing doesn't exceed 200 to 300 revolutions per minute, or RPM. Finally, lubrication doesn't have to be done as often with grease as it does with oil. So grease is commonly used in situations where frequent oil lubrication is difficult to accomplish. In this part, we'll look at some typical examples of how to apply grease for proper lubrication of industrial equipment. Sometimes workers apply grease manually with a brush, clean cloth, or their gloved hands. The workers must use the required personal protective gear and make sure that the equipment is turned off, locked out, and tagged before they apply the grease. Sometimes workers apply grease to operating equipment by turning a screw-type cup to force grease into a component such as a bearing. The level of grease in the cup must be checked regularly. If the level is low, the cup must be refilled. Anti-friction bearings often have housings that retain grease and help keep out dirt. But a problem can occur if too much grease is put into the bearing because there's no place for the excess grease to go. Consequently, a way for old grease to leave the bearing must be provided. In this example, the housing has a drain hole. To prepare to grease the bearing, remove the plug from the drain hole and wipe the grease fitting clean. Then connect the grease gun to the fitting and slowly add the specified amount of new grease while the machine is running. Don't overgrease the bearing. Typically, with a hand-operated grease gun, you should apply no more than 3 shots of grease at a time. Next, disconnect the grease gun from the fitting and wipe the fitting clean. Then, allow the machine to run for a few minutes with the drain plug still removed. As the machine operates, excess grease will be forced out of the drain hole. After a few minutes, wipe the drain plug clean and put it back in the drain hole. Greasing a sliding surface bearing, such as this plain journal bearing, is a relatively simple procedure because the design of the bearing housing doesn't cause grease to be retained in the housing. The usual practice is to apply grease to a grease fitting on the housing with a grease gun while the equipment's shaft is turning. This procedure is generally continued until new grease is forced out of both ends of the bearing. Any excess grease will rapidly work its way out. In this topic, we talked about oils and greases and some of the different methods for lubricating equipment with these types of lubricants. To check your understanding of the material that we covered, try answering some practice questions.